Hello, my name is Mohammed Shahra, and I'm going to tell you about our work with Samuel Ninkiti and Riccardo Bianchini on how to provision differentiated last level cache allocations to VMs in public clouds. This work was conducted when I was at Microsoft Research, but today I'm recording this from the UBC Vancouver campus, and I should acknowledge that the campus sits on the traditional, ancestral, and ceded territory of the Musqueam people. Let's start first talking about last level cache. Last level cache is a shared resource on modern microprocessors. Each core might have its own local caches, but to facilitate core-to-core communication, there is usually a shared last level cache before we go to main memory. In terms of performance, last level cache is very important because while access to last level cache would be in the orders of nanoseconds, going to the main memory takes much longer. At the same time, last level cache takes a considerable amount of space on modern processors. Thus, it directly maps to the cost of processors. It can also be a source of noisy neighbor effects. This means that a process's cache line can be evicted by competing processes. A solution that has been known for a while is cache partitioning. So there are techniques in software or hardware to be able to partition and limit how much of the last level cache is given to each process or each VM or each application. Software techniques include page coloring, and hardware techniques include a technique called way partitioning that is now available on modern CPUs. Let's look at the Intel cache allocation technology to understand how way partitioning works. So for your last level cache, you have a number of ways, and then also you have a number of classes of service. So what you can do is that you can assign each of your logical CPUs to a consecutive set of ways. And this way, when each process is running on a CPU, you can limit it to use a specific portion of your cache. There has been a rich body of work applying last level cache partitioning techniques to make applications run faster, higher throughput. Unfortunately, none of them quite maps to the requirements of public cloud VMs for two primary reasons. One is that they are all profiling based, and also they often work at the node level and are opportunistic. So typically in public clouds, virtual machines are opaque. We don't know exactly what is running inside it. Or even if we can get some profiling data, we cannot really map that to the expectation of the user. Let's look at an example. Let's say that we want to use instruction per cycle as a metric of progress for our applications. Is it a good metric to be used in public clouds? No, because the VM could be just busy waiting on a lock. Without knowing the application or knowing the user valuation for increased IPC, it's meaningless. Another example, let's say that we were to use a profiling-based approach in public clouds. If I'm a developer, I could easily have random accesses, I get cache misses, and I can trick the provider to give me more last level cache. This selfish behavior would give me more cache, but puts pressure on my co-tenants. These are just two examples demonstrating why the profiling-based approaches are not quite suited for public cloud settings. The second problem that I mentioned is operating at the node level. When you're operating last level cache partitioning mechanisms at the node level, you are bound by the mix and number of co-tenants. It's much easier if the scheduler at the cluster level is aware of this and just simply doesn't co-locate those VMs or applications that have high demands. That way, the node level policy can also work much better. Another issue with operating at the node level is that you cannot really deliver consistent allocations, and that is very important in public cloud settings. However, that enforcement requires your scheduler to be aware of last level cache. Over the past 6 years or so, there was a rich body of work looking at the settings where the application is known, or at least profiling is meaningful, and everything happens at the node level. But we think also there is room for looking at settings where application is unknown, profiling is meaningless, and your scope to enforce a consistent delivery of last level cache allocations is beyond just one node. In that angle, we have been working on this system called CacheSlicer. First, we look at how we can define last level cache allocation metrics that are workload agnostic. The second component of CacheSlicer is optimizing last level cache allocations for, by default, 3 categories of VMs. We deliver full isolation to cache sensitive VMs, best effort isolation to standard VMs, and full sharing to low-cost VMs. The third element of CacheSlicer is integrating last-level cache management into the cluster-level VM scheduler. Let's look at some of the primary workload agnostic metrics that we use. There are more metrics defined in the paper, but here I described the two main ones. First one is called ways per core. So it's basically normalizing the amount of cache allocated to a VM to the number of cores it has. It is basically a way of enabling us to compare smaller VMs to larger VMs and having a fair allocation across all different sizes. The second metric is called resource competition factor. It quantifies the competition as a function of LLC vary sharing. While the exact formula is in the paper, it captures how much pressure LLC allocation of a VM is receiving from other VMs. Intuitively, if RCF is 0 or close to 0 means that you have a very good degree of isolation. And as RCF goes to 1, it means that your LLC share is under more pressure from the co-tenants. On the right, you see the distribution of RCF for Azure clusters over a day. These are clusters with different hardware generations and across different parts of the world. But you can see that the pattern of competition factor is very similar between them. Majority of VM experience RCF greater than 80%. Part of our system is about conducting this optimization where we have to understand how much last level cache we can assign to different standard VM types. Because with the full isolation of the cache sensitive VMs, here the question is how much we should give to standard VMs. The trade-off here is that if you enlarge these standard VMs allocations, they're going to have overlaps with themselves, and also they're going to suffocate those low-cost VMs in terms of how much cache is left for them to share. We want to assign a last level cache size to each VM type. Similarly, as to the current systems where each VM type, it comes with certain number of cores and certain amount of memory. So here what we look at is the distribution of VMs, and we look at the real traces, and we have this optimization platform that starts and explores giving more or less ways to each VM category and tries to minimize the cost function. You can see the example cost function. The goal is to increase the allocation for standard VMs and reduce any amount of competition between those, and also make sure that there is not a lot of pressure on the low-cost VMs. The optimizer explores different LLC allocations to each of those standard VM categories, and eventually we land on some place that we have a good balance between how much we increase their way per core. Here we started from ways per core of 1, and we increased it almost 45%. Also, we try to make sure that the resource competition factor between them, we will minimize those. There is also a scheduler that now is LLC aware. We added 2 rules to the scheduler to enforce that the cache sensitive VMs get all the resources that they need, and the standard VMs and low-cost VMs have a minimum contention. To find what changes we made to the scheduler, please look at the paper. This is for 720 nodes for a period of 2 weeks, where we have a billable utilization of 85%. Each server has 40 cores and 40 last level cache ways. Here we have this mix of different categories where we have 3% of the VMs be cache sensitive. These are premium VMs, more expensive. 20% of the VMs are a standard, but because they're larger size, they take 61% of the cores, and then 76% of the VMs are low cost. These are small VMs that are cheap, and they only constitute 35% of the cores. Now, in the paper, we look at different mixes, and we also explore the effects of that into the system's performance. What here I'm going to show you is 2 numbers. One is how much isolated ways per core a VM gets, and there's the expected ways per core. So this is basically the statistical average of how much LLC they're going to have access to during their lifetime. Not that if the isolation is very smaller than expected ways, it means that there is a high degree of sharing going on. So here you can see to the very left, the distribution of EWPC and IWPC for the current state of affairs, where there is no LLC partitioning. As seen, almost all of the VMs have IWPC almost 0, meaning that they're all doing some sharing. that the small amount of VMs that are not doing sharing, those are just the largest VMs possible, and they take the entire server, and that way guaranteed no sharing. With CacheSlicer, we can create these differentiated regions in this distribution. And if you just look at each category separately, you see that low-cost VMs still have very low isolated waste per core. Cache-sensitive VMs, they have isolated waste per core that is equal to their AWPC. And for a standard VM, there was some upsizing going on. Some of them were upsized to have 1.25 waste per core. Some of them had upsized to have 50% higher than where they started. But the good thing is that here, the IWPC gets very close to the expected waste per core, but sometimes the VM scheduler cannot prevent those contentions. So there are many more evaluations in the paper. Some things that I didn't talk about is how we handle partial last level cache overlapping at the node level. We conducted numerous sensitivity studies, and we also looked at a number of applications to understand how CacheSlicer affects their performance. There's this one result, I think it is worth looking at it together. And that is about how we compared with the node level policies. It's a little bit comparing apples and oranges because the node level policies are at the mercy of the mix of co-tenancy you'll get for a server. We first took 4 applications. We analyzed their sensitivity to last level cache, as you can see on the left subfigure, and we got the needs for those curves. That determined the baseline for performance. We then created the worst case and best case scenario of co-locations among these applications. And as you can see to the right, the navy blue is where we have the node level policies in terms of relative performance range compared to the stars to the left subfigure. You can see that the CacheSlicer for cache-sensitive VMs, that range is very minimal. Here, there is variation because last level cache is not the only source of performance degradation. There's also a memory bandwidth. There are other sources of noise effect, but last level cache is the primary one. Assigning these workloads to be cache sensitive on CacheSlicer, this range of performance shrinks by a lot. So in conclusion, we believe that there is more research required to be done at how last level cache partitioning should be done at public clouds, where applications are unknown and where profiling is not quite feasible. And with this vision, we went for designing CacheSlicer, which defines workload agnostic, profiling-free metrics, comes with an LLC-aware VM scheduler, and an optimization framework to find the best allocations to VM categories. We have evaluated CacheSlicer in different scenarios and observed that it can achieve delivering differentiated last level cache allocations in a consistent fashion. With that, I'll be happy to answer any questions, and thank you for your time.